Episode 14: Pigment Interactions. Synergy between multiple pigments in multi-layer systems in automotive coatings. In this episode, we explore pigment interactions and how multiple pigments work together in multi-layer automotive coating systems. Modern automotive finishes often rely on a combination of color pigments, effect pigments, extenders, and functional pigments across primers, basecoats, and clearcoats. Understanding how these pigments interact is critical for achieving optimal hiding, color consistency, gloss, visual effects, and durability. When multiple pigments are combined, their optical and physical interactions can enhance or hinder performance. For example, titanium dioxide as a high refractive index white pigment provides opacity and brightness, while carbon black contributes depth and contrast. The interaction between TO2 and carbon black can influence jetness, hiding power, and visual uniformity. Organic pigments contribute chroma and hue, but they are more sensitive to environmental stresses and can be affected by other pigments if dispersion or compatibility is not properly controlled. Effect pigments, such as metallic and pearlescent flakes, are particularly sensitive to interactions. Their optical properties depend on particle alignment, orientation, and layer thickness. The presence of fillers, extenders, or other color pigments can influence flake orientation during application and leveling, affecting brightness, flop, and color travel. Layer sequencing in multi-coat systems, primer, surfacer, basecoat, and clearcoat, also determines how effect pigments interact with underlying colors to produce the desired visual effect. Extender pigments, including talc, clay, silica, and calcium carbonate, interact with other pigments primarily through physical mechanisms. They modify pigment packing density, influence rheology, and can enhance or reduce hiding and gloss depending on their refractive index, particle shape, and concentration. Extenders also impact the distribution and orientation of effect pigments, making them an essential consideration in multi-pigment systems. Functional pigments such as IR reflective, conductive, or anti-corrosion pigments introduce additional interaction considerations. IR reflective pigments must maintain optical performance without compromising effect pigment appearance. Conductive pigments must form continuous networks without affecting visual uniformity. Anti-corrosion pigments, particularly in primers, must remain compatible with topcoat pigments to prevent color shifts or defects. Proper selection, surface treatment, and dispersion are critical to managing these interactions. Pigment interactions also influence pigment volume concentration, PVC, and critical pigment volume concentration, CPVC. The combined volume of multiple pigments affects binder coverage, film integrity, and porosity. Overloading or improper balance can lead to defects such as reduced gloss, flocculation, or microvoid formation. Formulators carefully calculate pigment loadings to maintain CPVC below critical thresholds while achieving desired visual and protective properties. Chemical compatibility is another important factor. Pigments may interact through acid-base reactions, ion exchange, or surface adsorption, affecting dispersion stability and long-term performance. Dispersants, surfactants, and surface treatments are used to prevent flocculation, agglomeration, or color shift. Pigment surface chemistry must also be compatible with binder chemistry and other formulation additives to ensure consistent optical and mechanical performance. Rheology and flow behavior are strongly affected by multi-pigment interactions. High aspect ratio flakes or plate-like pigments can increase viscosity and thixotropy, influencing leveling, sag resistance, and application uniformity. The combined effect of multiple pigments on rheology must be managed to maintain consistent film thickness, smoothness, and defect-free application, particularly in large-scale automotive production. Layer sequencing in multi-coat systems is essential for managing pigment interactions. Primers often contain anti-corrosion pigments and extenders to provide mechanical and chemical protection. Basecoats contain organic, inorganic, and effect pigments for color, opacity, and visual effects. Clearcoats protect the underlying layers while enhancing gloss and depth. Each layer must be formulated to complement the others, ensuring consistent color, appearance, and durability across the vehicle. Optical interactions are critical, particularly in high-end finishes with metallic or pearlescent effects. Layering pigments can create interference, depth, and visual complexity. For example, A darkened basecoat can enhance metallic contrast, while a light basecoat can maximize pearlescent shimmer. Flake orientation, layer thickness, and pigment packing density determine how light interacts with the film, affecting brightness, flop, and color travel. In summary, multi-pigment interactions in automotive coatings are a complex interplay of optical, chemical, and physical factors. Color, opacity, gloss, effect, rheology, and durability are all influenced by how pigments interact within a layer and across multiple layers. Mastery of pigment synergy allows formulators to achieve consistent, high-performance coatings with the desired visual effects while maintaining mechanical and protective properties. If you have any doubts about pigment interactions, layering effects, or multi-pigment system design in automotive coatings, leave your questions in the comments and I will clarify them.